Hello, everyone. We will start today's session. And actually, as I said in the previous lectures, starting from the last lecture, which is a guest lecture, we are talking about different game theory scenarios. And then we are trying to analyze in those scenarios what are possible, what are not possible, and what concepts are interesting, and how to adapt certain existing concepts to the new scenarios we may encounter in real life, right? Okay, now today actually the topic is called fair division. And actually this is the, you can say the very large subfield of game theory, which is very useful in practice and has very nice and elegant results for different settings. And actually, well, some of them are very easy when you, well, see the problem, but actually the solution is very, very non-trivial. Okay, now for fair division, I adapted the slides from Xiaohui and Bo's slides, and they too are two young people working in this field, and actually each of them, they're focused on different subfield, and they are doing very nice work. Now we will start with the traditional fair division, which well, actually has existed for many years. Okay, now fair division, it has something to do with the resource. Whenever you have something, some resource to allocate to different people, then you will have this problem. All right. Now, for example, when you rent an apartment, you may rent the apartment with another friend or another person. But when you share the renting, then how to share the rent, right? The money you need to pay for the apartment. That's an important question, right? And then also when you take a taxi, so there are kind of two people who do not know each other take a taxi from one destination to the other. One of them may get on the taxi in midway, right? And then how to share the taxi fare. This is also some problem that's very realistic, right? And then also when you are doing group project. Now, although in this course we do not have group project, but in some other courses there may be group project. And then we do group project, how to assign credit to different individual, right? How much contribution each of you make to the project, and what's the mark you will get for the project, right? And also you may have some kind of writing papers together, right? And then who will be the first, who will be the second author, etc., etc. And then also, well, these three are some, you can say, the modern days resource allocation, but there are also some old days resource allocation, like dividing goods, or like jewelry, or toys, furniture, etc., etc. And these things, they are some kind of a standard goods, right? So they are useful to some people, right, to different extent, and then how to divide them to different people so that they're happy. Okay, now, of course, when we talk about the goods, then the other side will be the so-called bads, right? The bads, usually we do not call bads, we call it chores. And actually, chores is the focus of the next lecture and sometime further on, all right? So today we'll be focusing on goods. Basically, we are dividing things which are useful to people, okay? Well, now, actually, before I move on, there's one last thing, which is also interesting, but we will not cover it here, is about the last question mark, right? So basically, it's about maybe some of you have some idea about some new app that may be useful, all right? And then, well, what kind of app will eventually be developed? This is an interesting thing, right? Because different people think that different things will be useful. And then if only one app can be developed, then which one, all right? You try to make that final agreed app to be, well, somehow useful to everybody in some sense, right? Okay, now, so this is another bigger agenda, which arises from this fair division research problem, okay? Well, so I hope that the background is clear enough. And then we are trying to start with the so-called classification of the resources. Now, on the left, you can see it's some kind of land, right? And this land, we can consider it to be somehow divisible because you can cut the land along any boundary. Now, usually it's okay, right? Okay, I say, I cut it in the half place, or I cut it in 1/3 place, etc., etc. So basically, this kind of resources, we say they're divisible resource. So you can divide it into any granularity, right? Okay. Now on the right, you see what? You see paintings, right? So for paintings, we call it indivisible goods because, well, for one painting, if you divide it, it will be useless, right? So basically, you want to keep the whole of one painting. You either get it or do not get it. Okay, so this is indivisible resources. So basically, we have two kinds of resources. And then we start from the easy one. So which one do you think is easier? Dividing what kind of resource will be easier? Have a guess? Okay, so I see some answers. Divisible, okay, yeah, right. All right, so divisible resources will be easier. So the reason is that many good properties you can guarantee without sacrificing too much, okay? So let's start with the very, very famous example called cake cutting, all right? Now, the reason we study cake cutting is that, well, actually it abstracts the essence of the divisible resources, okay? So we here assume that we have a single heterogeneous good, all right? And this resource is divisible, and we represent it by an interval from 0 to 1. All right, and then we have a bunch of agents, and these agents are labeled as 1, 2, 3 until n. And then this cake, so the cake, well, the whole cake is 0, 1, but you can cut an arbitrary piece out of it, right? So we say a piece of cake, x, which is a subset of the interval 0, 1, is a finite union of disjoint intervals, which means, well, actually, I can cut the cake in an arbitrary place. And finally, if I give you a piece of cake, that means I give a union of those intervals to you, right? So for example, I cut it at the point of 0.001. Every 0.001, I make a cut. So basically, you see 1,000 small pieces. And I can give, for example, 20 of them to one agent. And then these 20 can be spread along the interval. They do not need to connect to each other, okay? When I say I give you a piece of cake, it does not mean that I give you a whole piece, all right? It means that I just give a collection of pieces to you, all right? So we are making some kind of small adjustment here. Usually we say piece of cake just means you use a knife to cut the cake into several pieces and give you one piece, right? But here we do not mean this, okay? So we are giving some part of the cake to you, and that part we just simply say it's a piece of cake, okay? Now, what's the goal? So the goal is now you have n people. I want to cut the cake in such a way that I give each of the n people one piece of cake so that they're happy. All right. Now, of course, you cannot give the same part to two different people, right? So you have to make all the AIs disjoint. Okay. So they should not have intersection. And also, I guess that anyone notice some typo on this? Oh, actually, it's not typo, right? So actually, mutually disjoint means the intersection of those AIs are empty set, right? And furthermore, we also require the union of these sets to be 0, 1. In other words, you cannot throw away some piece of cake. Okay, you have to give all of the cake to all people, okay? So no waste. All right, now, so up to now, I have explained the basic setting of the cake. Let me see one question. Are there any research taking the noise in cutting cake? Oh, okay, very good, very good question. So because I do not specifically work in this field, so I cannot answer the question 100% sure, but according to what I read, no research is dealing with the so-called noise in cutting the cake. So I guess Ziao is asking about something like when I cut when I cut the cake, maybe the piece itself has some kind of a possible distribution, right? So I make a cut here. Maybe, well, my cut is not so accurate. I'm trying to cut in at the 0.001, but actually it turned out to be 0.0011, right? So there's some kind of error. Do you mean this? So your intended cut. Oh, okay. Well, I guess this is a very interesting question. A very unique angle. Let me take a look. Now, after we explain all the necessary or all the useful concepts in cake cutting, you may take a look in this problem. That's very interesting, I think. Okay. Now, now before I move on, all right. So I would like to just ask you for the understanding of the basic setting. So is the cake cutting scenario clear? Now, we didn't talk about the objectives yet. All right. So just the general picture. Okay. What are we trying to do? We are trying to divide the cake or allocate the cake in some way to some people. All right, such that some nice properties are satisfied. But this nice property, we didn't talk about it yet, right? So we are going to that very soon. Okay, so I end the poll, and then it seems that majority of you get the idea. For the very few of you who didn't get the big picture yet, maybe it's just because we didn't move on to the concrete objective yet. Okay, so let's see further definitions. Now here, the reason we say it's a heterogeneous cake is that different people will have different feeling towards the same cake, right? Okay, for example, for one, for the real union is not one. Let me just answer this question before I move on. So, Zhengwei, you ask why the union is not one. So, which part? Are you talking about this union of AI is equal to 0, 1? Yeah, so the union is the whole cake, right? So the whole cake is the interval 0, 1. And then we require the union of all the piece of cakes to be the whole cake. We cannot throw away anything. Is it clear? So the union is actually 1, is the whole interval. Okay. Well, the whole thing is an interval. Okay, basically, you can consider. Let me just. Where is my pen? Okay, here. Yeah. So we are dividing what? We are dividing interval. Yeah. So I guess that's the many of you are discussing here. It's very good. So basically, we consider the cake. So here, the 0, 1 is just a one-dimensional cake. Usually, the cake I show you here in the picture, it's round, right? But well, if it's a round cake, it seems too complicated. So we just simply simplify it to be an interval 0, 1, which is the interval I draw here. All right, the red interval. Okay, and you are trying to divide the interval into several pieces and give one piece to the first agent, the second piece to the second agent, and so on. Okay, so this is what you do. Therefore, we assume that we cannot throw away any cake for now. All right, we cannot throw away any cake. You have to give the cake anywhere, any piece of the cake to someone. Okay, you cannot say, oh, this piece I just keep it here. I do not give it to anyone. This is not allowed. All right. Okay, so is it clearer? Oh, okay. So now I get the point. Okay, so Jing Peng also asked the same question, similar question. Why the union is not always 1? Okay. Now because later on, when we move on to more advanced topics in the cake cutting, sometimes we actually not more advanced. So in order to have easy results, sometimes people will assume cakes can be thrown away. So when you can throw away the cakes, then the union is no longer 1. Okay? Yeah, everyone will get some piece. And then sometimes people have assumption. They say, okay, we allow throwing away some cakes. Okay, we allow somebody some cake in the end turns out not to be allocated at all. Okay, so some version of the problem assume this, and then when that happens, you can imagine the union is no longer 0, 1, right? It becomes a subset of 0, 1. So I guess that's the question some of you are asking just now. Is that right? So that means this condition is necessary. Okay, it's not always true, but sometimes if you do not allow the cake to be thrown away, and then you have this kind of requirement. Okay, so is it clear now? Especially Jingpeng and yeah, Zhengwei, Jingpeng and Zhengwei. Is it okay now? Yeah. So okay. So remember, this is an interval, right? So this is the interval from 0 to 1. So this point is 0 coordinate, and this point is 1. Okay. All right. Okay. So this is the interval, and that's why we say we do not say the union is 1 because yeah. So the interval has a length. So that's why it is different from the absolute value. Okay. Yeah, you're welcome to raise any further questions while I slowly move on because yeah, so we need to have this whole setting clear, right? Because we are trying to say that the whole cake, right? It is we have heterogeneous agents, which means different people have different preference towards different parts of the cake. For example, let me go back to the cake again. Now, in this cake, you may have some kind of well, berries on the cake, and somewhere is a cream, and then maybe some agents like cream a lot. They don't like berry at all. If you give him berry, he will not be happy, right? And then some other agents may say, oh, I like berry more. I do not like cream. Okay, so that's why for the same piece of cake, for example, from 0.1 to 0.2, right? This piece of cake, some people say, oh, this is very valuable to me, and some other people may say, useless. Okay, I value it 0. So that's the setting of so-called heterogeneous cakes. Okay, yeah. Yeah, feel free to ask questions in the chat if anything unclear about the explanation or the model. Okay, and then this valuation function has to satisfy some nice properties. Now here we have 3 properties you need to satisfy. The first one, additive. So additive means if one piece, I think its value is alpha, a second piece, I think the value is beta. Now if I get both pieces, then my value should be alpha plus beta. So I think this is pretty clear, right? So basically it just means that I can add the value of different pieces together to be the value of the whole thing I get. Okay. Now second one is normalization. So which means the whole cake to every agent, its value is 1. All right. So that comes to some of your question earlier, probably is because of this. So we have a cake, which is described by the interval 0 to 1, and everyone, his or her value towards the whole cake is 1. But he or she may prefer different parts of the cake. That's okay. As long as the whole thing add up to 1, it's fine. So basically, we are doing the normalization for every agent. Okay? Yeah. Now the third one. The third one is some nature about the so-called divisible resource. All right. So it basically says if one piece of cake, its value to me is alpha. Right. So this value to me is alpha. Then I can always find a sub piece of cake whose value to me is lambda alpha. And this lambda can be any value between 0 and 1. Okay. Oh yeah. So this is the assumptions, all right, the 3 properties that the valuation function need to satisfy. And the C9 is asking, on the contrary, the measure of vacant set must be 0. Yes, you're right. Okay, so if I get nothing, the value must be 0, right? Okay, yeah. Any question about the 3 properties? Okay, now is a very tricky problem. if an agent tells you his or her true preference, then it may be too much input. Why? Because you see, agent's preference towards the cake can be very, very complicated. He may say, from 0 to 0.000001, I think the value is something, right? And then 0.00001 to 0 point something is another value. So basically, if you ask the agent to tell you the whole piece of information, then the input size will not be any reasonable number. So that's why we here usually adopt the so-called query complexity. So it means how many queries I need to ask the agents such that in the end, the allocation I have will be somewhat good, right? Okay, so what kind of query are possible? Now here, people use a very well-known protocol or query model called Robertson Web model. So what's that model? The model is very easy to understand. It basically will tell you the answer of two queries, two types of queries. The first query, I put as input an interval xy and ask the oracle. Can you tell me, this agent I, how much value he or she thinks this piece is worth? Okay. Now, so this is so-called evaluation of I towards the interval xy, right? Now, in short, we can just say vixy. So the value, right? Value of I towards the interval xy, right? Okay, and then the oracle, so here the query oracle tells you, okay, his value is alpha. Now, this is some answer you may get from the query oracle. Now, this is first thing. Now, second thing is another one. It's called cut query. What's a cut query? So cut query is just reverse the operation a bit. It says, okay, I ask you if I fix a starting point x and I fix a value alpha, can you tell me where should I cut the cake? Okay, so basically this one, his input is the starting point x and the value alpha, and the return value will be the right endpoint such that xy, its value is exactly alpha to agent I. Okay, so remember two kinds of queries. One kind, I give you a piece, you tell me what value this agent has. Second, I tell you a starting point, and then I also tell you the value I'm expecting. And then I ask you, oh, where should I cut the cake so that that piece will be worth alpha to that agent I. Okay, and these vixy, they are not this question is very philosophical, okay? Subjective or objective. Okay, so we can say they are objective, but different people have different objective feeling, right? So so they are, or I can say they are treated as input. Okay, so basically these are input. They're already there, right? Different people have different feeling towards different parts of the cakes. These things, they are all already fixed. You cannot say, I think this piece of cake is 0.1, but I tell the system it's 0.2. Well, that may not be good. But we also come to that part. This is about the strategy proof or truthful analysis. Okay, but for now, we assume that all these information, all right, they are already in the system. The only thing is you do not know them before you make the query. After you make the query, you know the value. All right, so is it good enough? Okay, good. So now, let's move on. Now, basically, the central topic today is fair division, right? So the main word is fair. The main word is fair. So what are the possible fairness properties? Now here we have two very, very classic fairness properties. One is called proportionality. So proportionality means everyone gets at least 1/n value of cake. So you remember we have n people, right? So if you have n people, your total value towards the cake is 1. Then very naturally, if you get 1/n value, you should be happy, right? Because you get already at least the average of what you expect to get, right? Okay, so everyone gets at least 1/n will be a very good solution. But of course, even if a solution satisfies this, some of you may still think it's unfair. All right, it's very likely. For example, you get 1 over n, and the other person get n minus 1 over n, right, of his value. You may think, oh, you may get jealous, right? So why he gets so much, right? I only get average. He or she gets so much. Okay, but that's another story. Okay, we'll discuss a bit in the next concept. Okay, so proportional requirement. You see, it's very reasonable, and at the same time, it's also very friendly towards the solution. Why? Because proportional solution always exists and are easy to find. Okay, now we'll use some examples to explain why it exists. Yeah, very good. So you ask why it always exists, right? Okay, so this one, although we are not talking about the general existence results, but we'll talk about some special case. Okay, it's a very good question. We'll come to it very soon. And then another concept is called envy-free. So envy-free basically says any agent will not envy any other agents. How to define it? Well, the way to define it is actually very easy. You see this line? Now, we are using VI, which is the value function of agent I. And AI is the bundle agent I, or the piece of cake agent I gets. So this definition says, agent I get a piece whose value is at least any other piece other people get. Okay? But remember, we are using the same I here. We are not using J. We are using I. So basically, in one agent's view, he sees n pieces. And he thinks, oh, the piece I got is the best among all the pieces. So that's the envy-free. So basically, for other people, right, they get some other piece. But this agent I will not envy him or her because he or she thinks that other piece does not have a higher value in I's point of view, right? Okay, so basically, I does not envy other people because he or she thinks the other people didn't get a better piece than he or she gets, right? Okay, so this is envy-free. But envy-free, you can see some interesting connection to proportionality. First thing, if some solution is envy-free, it must be proportional. What's the reason? Okay, you just sum up all the entries of the two sides of the inequality, and here this one becomes n times vi ai, and that the other part becomes the whole value, the whole cake, right? The other part becomes whole cake. Remember, the whole cake is 1, right? Value is 1, so vi ai will be larger than or equal to 1 over n, right? So basically, if your piece is no worse than other pieces, then your piece is at least average, right? Otherwise, it's not possible. Okay, so that means envy-freeness will imply proportionality. Okay, and okay, and then Jiang Kun asks very good question. Remember, the cake is heterogeneous. For different piece of cake, people think differently, right? Okay, so you see, the whole value is 1, but this is for one agent, right? Okay, so suppose, for example, the first person get this piece. He thinks this piece is is half of his value. That's totally possible because he thinks the leftmost is most valuable, right? And then some people get this. He thinks this is already 1. The other one is useless, right? Okay, yeah. So okay, so it's good to know that you get the point. Now, subjective. This thing is very difficult to describe, right? So the values are different, but they are there already. You can also say they are subjective, but they are already there. You cannot change it. Okay. Yeah. Now, some other good news. An envy-free allocation in the cake cutting setting also always exists. That seems a bit more difficult to capture compared to proportionality. But anyway, let's just move on to some protocols which will give us the allocation which satisfy these two properties. Okay, then Jianchong asked a question. If somebody view a piece to be very valuable, but in others view his piece as 1 over n, will they envy? Well, so in general, will not, because people only envy because according to their own consistent valuation. Now, the example I gave you earlier is that maybe maybe A get a piece of cake he or she thinks is already half, and the other person get another piece which he or she thinks is 1. Then will this half one envy the other piece? The answer is no, because you already get half. So the piece the other person get will at most be half in his own point of view. So you will not envy, even if the other person thinks, oh, it's 1, it means a whole lot to me, right? But then that will not cause the envy to happen. All right. Okay. Well, so now in the history there are quite some classic protocols, and some of them you may already hear about it, especially the cut and choose protocol. I believe in your high school, some of you already have seen this kind of interesting problems. All right, so let's see. What is cut and choose? Now here we have 2 players, or 2 agents. And then in order to divide the cake fairly to 2 people, then a very, very natural protocol is that I ask the first person to cut the cake into 2 pieces. And then I do not let him or her choose. I will let the second person choose. Okay? Yeah. And then you see, then if you are the first person, if you don't know how the second person will choose, then what's your best strategy? You definitely cannot say, oh, I make the 2 pieces very different, right? That's not good, right? Because if you make them very different, then if the second people choose the better one of that, then you will feel sorry. So that's why the first person must cut right at half. So each piece means half to the first person. In this way, no matter which piece the second person pick, it doesn't matter, because anyway the first person can get half, right? Okay. Now, how about the second person? Well, second person, of course, it also has some advantage, right? It says, okay, since I can pick the better one, very likely the better one means more than half to me, right? Okay, so you see in this example, the second one will choose the one which means 2/3 to him, right? Okay, so he gets more. Well, now you see, cut and choose, it can give you proportional solution, right? Because everyone gets at least half. Also envy free, right? Because you see, first person will not envy because both pieces mean half. And then second person also will not envy because he already took the better one, right? Okay, so you will not envy the other piece. Therefore, you see, in this case, cut and choose can give you proportional and envy-free allocation. Now, in this case, they do not have the same linear value function. It's not true. And also, it's not linear, not necessarily linear. So in this case, you see this knife, he just stops at the middle point such that the left half and right half means the same to the first person. But the value inside the left half, the value inside the right half can be very, very irregular. All right? So the cake could be very irregular. It's not the linear function. It also they do not have the same function, right? Because the second person, you see, the left piece means only 1/3 to it, and the right piece means 2/3, right? So these 2 agents are different, right? This is something for sure. Second, the value function can be very, very irregular. We do not require anything about value function. So did I answer your question? Yeah, the same value for 1 does not mean the same value for 2. This is right. Okay, so which point you are not clear about? About the envy? You see that this left piece, it means half to the first agent, the red agent. This part means half to the also to the red agent, right? Okay, but this one means 2/3 to the blue one, and this one means 1/3 to the blue one. Okay, so if you are not clear about envy-free, then you can imagine the blue one takes this one. So this one goes to blue. And then this piece goes to the red player. Now for blue player, you will not envy the red player because the red player got a piece which only means 1/3 to it, right? You not envy. Oh, okay. So I see. Yeah, you got it. Right. Okay. Now, this is a first very easy protocol, right? Cut and choose. Now, second one is called Dubin-Spanier protocol. It's also the moving knife procedure. And actually, in a very recent paper, we are also using this moving knife procedure to design some new protocol for our problem, which is very interesting. Now, what's moving knife protocol? Now you see that cut and choose, it can only be used in the scenario of 2 people, right? If you have 3 people, how to extend? It's not very clear. But I remember for 3 people, it's kind of maybe some very famous IQ question you ever see, right? For 3 people, it's also already very complicated, all right? But still can be done. We are not doing it here, but it can still be done. But for 4 people, well, basically it's impossible. All right, very, very, very challenging. So it's not easy to extend. Now here, the Dubin-Spanier protocol, it can be extended to many people. So let's see what it does. Okay, so there is one central person. Now this time, not any single agent is cutting the cake. Okay, nobody is cutting the cake. Instead, there is some kind of central organizer. All right, he or she will move the knife from left to right, and then the protocol says whenever the knife moves to a point such that some person is satisfied with that piece, then the knife will stop. For example, you move the knife in such a way to some point, and then at that moment, the blue one thinks this piece is 1/3. Red one says this piece is 1/4. And the green one says this piece is 1/5. All right. So now suppose we have 3 people. So which person is already satisfied now according to proportionality? So here we are doing proportional allocation. Yeah, the blue one already satisfied, right? The blue one said, okay, I'm fine. I already got 1/3. I shout, please stop. And then the organizer will give the first piece to the blue one. Okay. Okay, this blue one. And then my knife continue moving, and then blue one will go out of the game, right? Because he already got a piece. And then say, okay, move. Up to this point, then the red one says, okay, this one is 1/4 to me. And then green one says, this is 1/3 to me. And then the green one will get a piece, right? Because he already satisfied. Yeah, so Jianpeng, you're right. The knife stop moving when somebody shouts, it's okay for me. And then it stop moving, right? So in the first round, blue one shouts, okay, this is 1/3 already. I will want the piece. And then the piece goes to the blue one. And then in the second round, you see the green one says, oh, this is already means 1/3 to me. So the second piece goes to the green one, right? Okay. And then the remaining will be the red one. Okay. Now, well, actually, it's very interesting and also easy to see. This one will give us the proportional allocation. Why? There's some logic behind. Not very easy, but also not difficult. Okay, why this whole thing will be proportional? Or why always somebody will shout, oh, you can stop now, I'm satisfied. Why? There is always somebody who will shout. Okay, yeah, I see quite some answers. Let me just go through them, right? Now, Wing Chun said everyone gets at least 1/n. Well, this is our conjecture, right? Okay, and then Jiang Kun said the former 2 get what they want. Yes, of course. But how about the last one? And then Ziao also said that except the last one, right? Everyone gets exactly 1/n, but the last one get more. Okay, good. So I see that yeah, so many of you are analyzing it, which is very nice. So basically, right? The important point is what? The important point is that if somebody didn't shout, then it means that that piece means less than average to the person, right? Okay, so for people who didn't shout, that means the piece that goes away is less than average. So when you have more and more pieces going away, the remaining thing must be more than average to him in the remaining pool of people, right? Okay, so that's why for people who didn't shout, their value, their gain actually could potentially be more, right? Okay, so that's the point, right? So basically, for example, here in this example, the blue one, well, when he shouts, of course, he get 1 over n. But for the red one and green one, what they lost is less than 1/3, which means the remaining piece means more than 2/3 to them. So definitely, when you further move the knife over, there will be some point where they will feel it's worth 1/3, which is average, right? Okay, so basically, all the people who remain in the system, the remaining piece of cake means more than k over n to those people, where k is the remaining people, right? K is the remaining agents who are still playing. And then, well, so that definitely in each future round, somebody will shout for sure, right? Because they definitely can get the average somehow, right? Okay, but well, it would be nice to have some kind of rigorous proof, but I believe that's not a big issue, right? I believe many of you can do this kind of proof. Okay, yeah. So now these two protocols, we just do a very brief analysis. All right, the first protocol, which person is in a better advantage in the cut and choose? Okay, so I see that second person, right? Because second person can sometimes get strictly larger than half, but the first person can only get half, right? Now, in this moving knife protocol, now again, somebody will get more benefit, which is again last one, later one, right? The last one can get the more benefit, right? Very likely. Okay, so this is somehow unfair because, well, it's a bit difficult to decide who to go first, right? Right? Okay. Well, but yeah, so that's a very nice thinking exercise for you, right? So to see who will have advantage in the whole process. But if, well, whenever somebody has advantage, then that means the whole system is a bit unfair because some people are, well, getting more out of this system, right? Now, and Wei Wei is asking, is it possible that the left part of the cake for the last one has a very small value? Now, a very small, even if it's very small, it's still larger than one. It's still at least 1 over n, as we just analyzed, right? Because every piece that is allocated to other people in the earlier rounds, this last person does not want that, which means those pieces are less than average. So in other words, the last piece must be more than average. Otherwise, you cannot add up to 1, right? Okay, so I hope that explained the concern, right? Okay, well, so yeah, good. Now, I would like to do a very simple polling. Is it okay up to now about the two protocols, especially for the cake cutting setting? Oh, very good, very good. Okay, yeah, thank you. I will end the poll. It's a very rare 100% clear. All right. Okay. Now let's move on a bit about the progress beyond 2 players. Okay. So in 1960, people developed or discovered a discrete envy-free procedure for 3 players. Okay. Wow. Actually, you see, this is not a trivial problem. For 2-person, cut and choose, naturally give an envy-free. But for 3 persons, it's only until 1960 people discover, oh, okay, we have some procedure to make sure 3 persons, when they play, they can also get envy-free result. All right. Now, in 1995, which is also not far from now, people discovered some unbounded envy-free protocol for any number of players, no matter how many. Okay, you have an unbounded envy-free protocol. So this is in terms of query. All right, remember we are talking about query complexity. How many questions need to be asked in order to get this kind of division, right? So unbounded means what? No bound. It can be 1 million. So if I say, is it always less than 1 million? No, not necessarily. Sometimes it can be larger. Is it less than 10 billion? No, sometimes larger. So there's no bound. It can be very many queries before you can arrive at envy-free protocol for this problem. Okay, well then they see, actually, why this problem is so hard, right? Okay, now very recently, only 5 years ago, Aziz and McKinsey, they have 2 publications in Stock and Fox, and you know Stock and Fox, they are top theory conference, which is very difficult to get in, and then they discovered some discrete and bounded envy-free K-cutting. Okay, but only for 4 players. In the stock paper, only for 4 players. Okay, for 4 players, for the first time, you have a bounded envy-free K-cutting protocol. All right, and very soon, now you know they're both 2016, so actually, I guess only several months, right? 3 months, and then they extend that to any number of players. Okay, well, so that basically, well, somehow solves the long-lasting open problem in the K-cutting history. Well, so there's one question from Xinran. Whether the people don't share their value function. Okay, it's a very good point. Actually, I'm going to talk about that. So basically, we can assume that they do not share the value function, and then especially agent 1 does not know agent 2's valuation, because if agent 1 knows agent 2's valuation, if you still use cut and choose, then agent 1 can make use of that to make himself get more, right? Okay, so that means in all the discussions we have until now, people do not know other people's valuation. All right. But this is a very good point. Actually, I didn't talk about it earlier because I'm intending to do it a bit later. Okay. Well, okay. Now I guess I will move on. Yeah. So here, there's one question about finite, bounded, discrete. Okay. So finite, it means it's not an infinite number. So the protocol will always end. And bounded means it will always end within a certain number. This number is fixed beforehand. Okay. And discrete, it just so actually discrete, it just means that it's kind of you can do it step by step. There, you do not need to involve under well, complicated procedure. Okay. Yeah. So which one is not discrete? So actually, Le Qian already bring that into discussion, right? Which one is not discrete? We have talked about 2. Yeah, very good. So Le Qian said that the moving knife, right? The moving knife is not discrete because you're moving the knife. But well, we are assuming that you can move in the knife very, very slowly until somebody shouts, right? Okay. So that's not good, right? So discrete just means, okay, I ask this query, ask that query, ask another query. So I just keep asking queries, and then you don't need to do things like the things that are happening in the moving knife protocol, right? Well, very good question, Shichen. Okay, and also thank you, Le Qian, for the clarification. Okay, so it may mean it's the end of the story because people already solved it, so everything settled. Actually not. The reason is, in the Stock and Fox paper, the maximum number of queries required by the protocol is this value. N to the 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 n. This is basically not possible. Even if n is 2, this is a huge number. All right. So that's why they are only of theoretical interest. In practice, you cannot do it, right? So there's a long way to improve it, right? Making it small. Okay. Well, so that's the open question left in this part, right? How to design an MV3 protocol with a small number of cuts. Okay. Well, so now before we take a break, we'll briefly mention the so-called incentive. So what is the incentive? It's the question I raised earlier, and some of you also raised related questions. It's basically whether I'm willing to tell the truth. All right. So in the last lecture, in the guest lecture, Taiki also talked about when you do auction or matching, whether the participants are willing to tell the truth, right? Whether telling the truth is the so-called dominant strategy, whether it's better than or it's no worse than any other strategy, right? Okay. Now, in the cake cutting protocols, the two, especially the two we discussed, then usually player can get benefit by manipulation. For example, cut and choose. So for cut and choose, player one can manipulate. Why? Especially when he knows the value function of the other player. All right? Okay. So that's why I say I choose to explain it here, because, well, suppose player one knows player two's valuation. He knows that player two will value the right half more. Then the player one can say, okay, then maybe at the first moment I move my knife a bit to the right. Then player two will still choose the right half, but I can get more, right? Okay. Now, of course, so that only says telling the truth is not dominant strategy. Sometimes not telling the truth is better, right? For this player, right? For this red player, if his cutting point is somewhere here, such that this part means half to the blue player, and then the red one will be better because he get more, right? He get this. Okay, so that's why, right? When he knows the other one's valuation, then he could get more, right? Okay, now about moving knife. Oh, very good. Okay, so Jiangkun, you are so fast, right? Okay, now this one also extends to Dubin Spanier, right? So for this one, you are doing this kind of moving knife. Okay, now for the blue player, he can shout later. Why? You see, the blue player says, oh, this piece is already good for me. But if he knows that the other two players, they still value the piece very little, then the blue player can say, okay, I just wait for a bit more moment, and then I shout. Then I get more than 1/3, right? Okay? Well, so now you see that actually in both scenarios, which one has more incentive to cheat? In a common nature of these two protocols? Yeah, earlier player or the player who are not advantages, right? So you see that in both systems, right, in both protocols, you see second player or the last player will have more benefit. For those people, they don't have incentive to lie because they don't need to lie. If they lie, they get less, right? Because if they shout earlier, they get less. That's not good, right? Okay, but for the one who start earlier, they will have incentive because they get the minimum, right? Just the proportional share, right? And they can manipulate, they can cheat such that they can get more, right? Okay, well, so I guess now we'll take 5 minutes break and then we come back. Okay. Yes, you're right. So Wing Chun said then the one who had advantage will be at the disadvantage status, right? And Xiao said if all earlier players cheat, they might not get 1/n. Yeah, so we are analyzing some special situation, but 1/n seems to be okay all the time because if earlier one cheat, they just cheat up to the moment that other people still did not shout, right? Because if they cheat, yeah, so I agree. So now I get the point. The point is if you cheat, probably you can no longer get 1/n because you face a possible threat that somebody will shout before you, right? For example, for the blue one, right? Say, okay, I wait. And then he wait until this point, and then somebody else shout. Oh, then he lose a piece of cake, which is very precious, right? That's not good, okay? Yeah, so that's a very good point. Therefore, those people, right, unless they know the full information of other people's valuation, in other situations, they do not have 100% guarantee that they will strictly benefit. Here, we are just explaining, well, at least telling the truth is not the so-called dominant strategy, because telling the truth is not always best, right? Given the agent's valuation profile. Okay? Yeah. So Wing Chong, I don't quite get what do you mean by everyone is optimally greedy. So can you explain a bit? Oh, I guess I know what you mean. Yeah. Now, two things, right? One thing is optimal greedy maybe means that the blue one, he will just wait until somebody will shout, but the blue one shout before him or her. Okay, so I guess that means the optimally greedy, right? And then, yeah, Lechen, you are right that Xuezhen's question about moving knife, right? Moving knife protocol is proportional, but not envy-free. It's not. It's definitely not envy-free, because especially earlier people will envy later people, because later people may get a lot, right? Okay. And again, just some remind during the break. Now, firstly, today's lecture will be 2 hours plus 1, which means 2 hours is on fair division, and 1 hour will be Q&A, and also explaining the tutorial questions. And then next week will be midterm, and the midterm instructions are already on the canvas, so you can practice recording during this week. Yeah, and then the remaining lectures, they will be on other than the fair division, we have facility location and also scheduling. Lecture notes of the last week is already uploaded, I think. It's not in the traditional format, but it's already uploaded. You may double check. I uploaded, I think I uploaded just on the same day. And Wing Chong asked, our exam will be in week 14. That's not possible, right? So any exam will be after week 14, not week 14. Did you know? Yeah. It's not week 14 for sure, right? Yeah. So in the lecture folder, there's one file which you may not know what it is. Then that's the lecture. That's the lecture slide of the last week. And then the coverage of the midterm will be up to last lecture. You're right. We will not test you fair division in the midterm. Okay. Yeah. Then let's move on. All right. So today's lecture, so just want to clarify. Today's lecture is week 9, actually, because we skipped 1 week in the earlier stage. So today is actually week 9 lecture. And yeah. Yeah, sorry, Xiao, for the laziness on my part for not renaming it. Okay, yeah. So wait. Yeah. So if today is week 9, then the exam is really in week 14. But in CityU calendar, today is week 10. So the exam is not in week 14, it's in week 15. And then that basically means that it's beyond the regular week 14 because we have a lecture in week 14, right? So the way I label my lectures, they are according to the original weeks. So we will see 1 week shift in the lecture number. Yeah. And then Xinju asked, is it proportional when someone is treating in cake cutting? You mean cheating, right? Well, it may not be anymore, right? If somebody cheats, it may no longer be well, proportional, because you may hurt other people's gain. Very likely. I don't know. Yeah, so it depends on, again, it's up. It'll be different for different protocols, right? Some protocol, even if you cheat, it's still okay, but some are not, right? Okay. Yeah, so I guess we'll come back to the, yeah, so basically, I guess I answered all the questions. Yeah. The final exam date, I don't know. Actually, some of you already know. I don't know. Well, maybe it's already released, but maybe not. But anyway, it will be in exam week. But which day? Actually, I also don't know. So maybe, well, okay. So some of you seeing aims, then it should be the right one. Okay. Yeah. Okay. So let's continue. All right. Now about truthful, we said that when do we say a cake cutting mechanism is truthful? If reporting the truth is a dominant strategy, which means no matter in which situation, the player will not gain anything by lying, right? So this is dominant strategy. And then actually we have already learned that the two protocols, the two famous protocols, they are not strategy proof, right? They are not truthful. Okay, and then the goal here will be to design deterministic, truthful, and fair cake cutting mechanisms. Right. So what are known? Well, actually, there are quite some negative results. For example, in 2013, there is a result saying that there exists no truthful, envy-free mechanism with bounded number of queries under the Robinson web model. Okay, so basically, it just tells you truthful and envy-free. They cannot be achieved at the same time unless you allow unbounded number of queries, right? So this is very strong negative results. Okay, now given such strong negative results, what's a possible way out? Well, one way is to maybe restrict the possible value function from agents, right? Because this impossibility results allow arbitrary value function from agents. So if we restrict the value function, maybe we have some positive results, right? And also the second way out is to let the players report full valuation. Okay, do not based on query. Just tell me full information, and then we make decision. Okay. Now, what's the possible restriction of the value function? Now, in cake cutting scenario, there are two very famous value function. One is called piecewise uniform. So piecewise uniform means agent's value towards any part of the cake is binary, either certain value or 0. So you see in this figure, right? It's either at this height or 0, right? And then he will tell you, okay, for these pieces, I value it to 1. And for other pieces, I value it to 0, right? Okay. Well, so this is piecewise uniform. Now, of course, it still satisfies the uniform requirement, right? So the whole value add up to 1 for the whole interval 0, 1, right? Okay. Yeah. So it's basically want or not want. Very good. Okay. And then there are some positive results. So they said that when players have piecewise uniform valuation, then there is a deterministic, truthful, and envy-free cake cutting mechanism. Wow, that's good. And also, it's not very old results. It's 2010. And actually, our group built further results on top of this. Now, their mechanism, they are doing the following thing. They say, okay, discard pieces that are not valued by any player. All right. If nobody wants it, just throw it away. Right. And then iteratively compute the best allocation. Right. So this way of iteratively computing best allocation, actually, it's the same algorithm as a scheduling algorithm I worked on about 15 years ago. All right. So it's exactly the same algorithm. So, but that algorithm applied to the cake cutting scenario, it can generate the truthful and envy-free cake cutting results. Okay, that's very magical, and that's also why I'm interested in this. So in 2015, we have one paper in EJKI considering a slight variant of the model where there is so-called externality. So basically, we just assume that, well, you get a piece of cake, okay, that's fine, but you also care what piece of cake other people get. For example, if your friend get a piece of cake which is very valuable, you will be very happy because, well, he or she is your friend, right? So basically, your value will not only be determined by yourself, by your own allocation, it will also be determined by allocation to other people. All right. So with this added complexity, we show that, well, this algorithm, right? This algorithm, it is still truthful when the coefficient of this kind of externality is very small. So which means if you do not care for other people a lot, then that protocol is still good. But if you care for other people a lot, then it's no longer envy-free and truthful. All right. So that's a very interesting follow-up result. The algorithm is not moving knife. The algorithm is so the algorithm is just something like you allocate a piece of cake to people who want it a lot. For example, let me just give you one example. Suppose someone wants this piece of cake, and someone wants this piece of cake. Someone wants this piece of cake. Someone wants a piece of cake. You see that we just okay, we try all the possible intervals and try to see for all the agents whose wanted pieces are totally inside my interval. I only consider them, all right? So I try all the possible intervals. For each possible interval I try, I will collect all the agents whose wanted pieces are totally inside this interval, and then add them up. And try to see the density, all right? What's the average, the largest density over the choices of interval? For example, the one example is if I use the interval here, right? If I use interval here, there are two people whose wanted pieces are totally inside. Then the density of this interval will be 2 over the length of the interval r. Okay, so there are 2 people wanting this piece of cake, right? Okay, and then if you have a larger interval like this, I have this interval, then maybe there are 4 people who are interested in this, whose wanted piece are inside this interval. Then it will be 4 over the length of this larger interval. So there are 2 over something, right? R1, and 4 over something. Now, among all these values, I take the largest one, which means which small area many people are competing. Then I first allocate this area to these people. And then later on, these people will be gone. Okay, I don't need to worry about you anymore. I deal with the remaining cake. And this exactly matches to the scheduling algorithm, which I studied earlier. All right, so this is the algorithm, but I guess the details of the algorithm, if you want to know it, you can refer to the 2015 and 2010 paper. They have description there. But it's a very good question, okay? Yeah. Now, actually, this also shows the beauty of research, right? So sometimes some 2 research subfields, they seems do not have any connection, but eventually the algorithms adopted are just identical. So that's some amazing connection, right? Okay. So now we come to the point which we have some confusion about earlier. It's called free disposal. It just says whether we are allowed to throw away part of the cake. All right, okay. Now, all the previous results assume that cakes can be thrown away, right? Okay. Now, but throwing away something may not sound good in some scenarios. For example, if you divide the land, all right, and say, okay, I throw away some land. Well, that may not be good. Then people will say, oh, you throw away this, then I will feel very unhappy. I would rather you give it to my opponent, right? Or I would rather give it to me so that I can define my opponent better, right? So something like this, right? And then if you, another scenario is about chore, right? So if you divide the tasks or chores, And then if you throw away something, then I say, oh, I just throw away everything, right? Nobody get anything, everybody will be happy. But that's not good, right? Because chores or tasks, they have to be done, right? If you throw away the whole thing, then it seems to be a very, well, naive and trivial results, right? Nobody will like it. So throw away something is some assumption made, right? The ability to throw away something is some assumption made in the earlier work, but well, they are not very well justified. Okay, so the goal here then will be whether it's possible to design deterministic, truthful, and fair cake cutting mechanisms without the free disposal assumption. In other words, you cannot throw away cake. You have to give it to somebody, right? Okay. Now, in Xiaohui's paper, they studied two players. It's also a very interesting algorithm. So suppose you have two players. They have piecewise uniform value function. Then what's the algorithm they design? Well, actually, very interesting. They call it eating algorithm. So eating algorithm means what? Means that you have two players. The blue player will start from 0, and the red player will start from 1, and they start to eat the cake at the same speed. Okay, what does it mean by same speed? I just move at the same speed. Right? But you see, they eat the cake at the same speed, but they will skip the cake they don't want. For example, for the red player, right, he will eat this piece, but he will skip this one. This one it will skip, right, and then continue eating here. So this eating algorithm will allocate the cake in such a way, right? So the blue one eat, skip something in the middle, and then continue, right? And the red one eat, and then skip something in the middle, which he or she doesn't like, and then continue. Now, at some point, they two will meet. Okay, they meet at this point, the green point. And then after that, the process stops. But remember, we do not allow free disposal, right? You cannot throw away the cake, right? You cannot throw the cake. So for those empty, jumped, or skipped pieces, you have to give it to somebody. But now we are not giving it to the blue one, because you see, for these two pieces of blue one, blue does not like it. So instead, I will give them to the red one. Okay, I'll give them to the red one, and then on the red part, the skipped piece, I'll give it to the blue one. So in this way, well, it will be good. All right, this allocation will be good. And then their theorem says this mechanism is truthful, envy-free, and Pareto optimal. Okay, so I'm not going to explain Pareto optimal here. I bet you know, right? It basically means there's no solution such that one person strictly gained but the other didn't lose, right? Okay, so this is their results. Well, remember, it's only for two players. For two players, it's already not quite trivial, right? Now, oh, you mean bar? Which bar? Which bar are you talking about? Oh, okay. Now, so you mean the bar here? Yeah, yeah. So the speed. So the let me just do this, right? Okay. So the speed is the yeah. So I cannot 100% recall the speed, but basically it should be something like value over time, I believe. Okay. So how much value I eat every second, right? So if somebody has a higher, so suppose the red one has a higher value for each piece he wants, and then he should be eating at a slower speed. Or not, sorry. Well, he should be moving on slowly, because every time he move forward, he get a lot, right? So that means the red one could move a bit slowly, right? Oh, okay. And then there is one question. Yeah, here we are drawing in such a way that value are the same, but in reality they could be different, right? No, binary does not mean the same, right? Binary does not mean the same. Binary just means that either my value is this or my value is 0. But remember, we have normalization. we need to make sure that the area under the curve, they are 1, right? This area should be 1, right? All these areas add up to 1. So if you are higher somewhere, then the duration will be shorter. Okay? So it's not the same value. All right? Okay, and also another question where we ask, both blue and the red player don't like the left bar. Okay, yeah, so now this also comes to Yang Ni's question, right? So basically, the bar means the eating. The red one is eating this piece and eating this piece, and then the blue one is eating this piece, eating this piece, eating this piece, right? And then the second stage, you see, we are doing this, right? Okay, you see this, right? So we are assigning those pieces skipped by the blue one to the red, and we are giving the pieces skipped by the red one to the blue. Well, the reason we do this is that if we give them to their respective user, for example, if we give the if we give this piece to the red, it means nothing to the red. Okay, but the blue may envy, right? If you give this one to red, the blue may envy because blue has a value here, right? Okay, so that's why we give it to the opposite player, such that, for example, if we give this piece to the blue, red will not envy it because red has no value for it. Okay, so that's why we need to allocate it to an opposite player. So I don't know whether I explain your question. Wait. Yeah. So we have 3 blank bars. Yeah. So, but the blank bars here, they are skipped by the blue one, right? So even if I give both of them to red, it doesn't matter, right? So we give it to the opposite player just to make sure the blue. For example, you give this one to. I get your point. You give this one to red, although red also didn't get any value, but at least blue will not envy red, right? So the main issue is if you give something meaningless to blue player to the other one, then blue player say, okay, fine. Since I'm 0, this one means 0 to me. Feel free to give it to other people. I will not envy them, right? Okay, yeah, good. Yeah, let me see. There are some questions. Start direction. Okay, Yixuan asked, does the start direction assign to the matter whether you eat from left or right? Yeah, so I guess it matters for the solution, but no matter which direction you assign to each player, the final result will be truthful and free. All right. Now remember, this is not the unique solution, right? So there can be more than one truthful and free Pareto optimal solution, right? So if you let them eat from different direction, then they will result in a different solution. Yeah, and oh, very good. Okay, so I guess you are just discussing to resolve that issue, right? Very good. And then and Yixuan asked how to assign the 2 starting directions for the 2 players. Oh, okay. So again, there's a question along the same line, right? So it's okay to assign any direction, so you can swap them too. So no matter which version you use, the result will be truthful, envy-free, and Pareto optimal. Okay. So, but there are 2 different allocations. All right. Okay. Good. All right. So, well, you see that this algorithm is also very elegant, right? So, but again, as we said, it's only for 2 players, right? It's only for 2 players. So that's why we have this open question, right? If you have 3 or more players with piecewise uniform valuation without the free disposal assumption, then what can we do? Is it true that there's no truthful envy-free mechanism, or there is something? Right? Oh, because I'm not doing research along this direction, so I also do not know whether this challenge has been addressed or not. Okay, if you are interested, you may take a look at the 2018 paper to see whether people solve this after that, right? So by checking citations. Okay. Well, now another kind of valuation function is called piecewise constant valuations. All right. So piecewise constant means what? It means this. All right. It means it's just a step function, right? So the red one, it can have a high value here on the left, and then becomes a middle value, and it becomes a low value, and so on, right? Okay. So this is piecewise constant valuation. And then piecewise constant valuation can be used to approximate general functions. For example, you have a very curved function, and then actually it can be approximated in the following way, right? Okay, well, so piecewise constant is also very useful, right? And then there are some negative results. Now, firstly, let's define something. It's called non-wasteful. So non-wasteful means no player receives any part of the cake with value 0. So if the player thinks this piece is 0 value, you cannot give the piece to this player. All right, so this is called non-wasteful. All right, do not give something to people who do not like it, right? Okay. And then there are two simultaneous efforts to solve the problem, to propose the negative results. So it says there's no deterministic, non-wasteful, truthful, and envy-free mechanism, even with only 2 players. Wow, that seems a very, very strong negative results, right? Okay. Now, there's also some other property called position oblivious. So position oblivious means that the player's value only depends on the length of interval he receives. It does not matter where that interval is. All right. So this is position oblivious. So it doesn't matter where these pieces are. As long as the total length is this value, then I think the value will be the same. All right. And then in their paper, also Xiaohui's paper, they show that there is no deterministic, position oblivious, truthful, and envy-free mechanism, even with only 2 players. Okay, so again, you replace the non-wasteful by position oblivious, it's still negative results. All right. Now, the most recent breakthrough is to remove those assumptions. All right. Non-wasteful, position oblivious, both of them removed. All right. So that result says there's no deterministic, truthful, and envy-free mechanism for 2 players for piecewise constant valuations. Okay, so basically this is a very, very strong negative results, right? Okay, so I guess for cake cutting or divisible goods, we just come to a stop, and then we will come to indivisible resource. All right. So for indivisible resource, the setting is also very easy to describe. We have a set of indivisible goods, 1, 2, 3 until m, right? And we have a set of players, 1, 2, 3 until n. And then they are not divisible, so each player will receive a so-called bundle. All right, this bundle mi. Now this mi need to satisfy again. It should be neutrally disjoint, right? No overlap, and also the union of mi should be the whole set m, right? And we well make the additive assumption. So basically, the value of I towards a bundle is the value of I towards any item in the bundle, right? We can just add them together. Okay. All right. So this is indivisible goods. And actually, you can see for indivisible goods, this description is even easier, right? But the solution will be harder. All right. Okay. So let's move on. Now, remember, please raise questions in chat if you are not clear about the setting. Okay. Well, so now let's see. In indivisible goods, what's the possible fairness measure? Now here, we introduce some other fairness measure. Now we know proportionality, so proportional is still okay. Envy-free, no, actually proportional, although it's okay, it may also no longer be useful here. So the main reason is it may no longer exist. For the cake cutting setting, proportional and envy-free, they always exist, right? Okay, although, well, didn't explain, but you can always find it. Well, you can find such existence results. But for indivisible goods, proportional allocation, envy-free allocation, they no longer exist. Okay, so can anyone give me a simple example showing the proportional and envy-free solutions may not exist? Oh, very good. Okay, so Wing Chun said only one item. Okay, so if you only one item, then you can only give the item to one person. Then the other person didn't get anything. So if the other person didn't get anything, then definitely it's not proportional because he gets 0, right? He didn't get 1 over n. And also, it's not envy-free because he envied the other person because the other person gets something, he didn't get anything. Now, it's not good, right? Okay, so that's why proportional and envy-free, these two fairness definition, they no longer work for indivisible goods, right? At least, well, in the extreme case, it does not work. Therefore, people designed or defined some approximated fairness guarantee. And this first one is called EF1, which means envy-free up to 1 good. In other words, it means that, well, if I'm a player, you are also a player, and then we get 2 bundles. And in what case I'm envy-free 1 of you? Okay, so only if, all right, if I remove 1 item from your bundle, I no longer envy you. Then I say it's EF1, I EF1 you. Okay, earlier envy-free means your bundle to me is worse than mine, right? But now it says, okay, your bundle, if I remove 1 item from it, then I no longer envy. Then we call it envy-free up to 1. Okay, so mathematically, it's the following. Suppose MI is the bundle I get, MJ is the bundle J get, then VI MI is at least VI MJ minus G. This G is a G I picked. Okay, is the item J is the item I picked. Okay, so when I is evaluating whether he or she should envy somebody, he gets that bundle and then choose to remove 1 item from the bundle, and then he sees that bundle. Okay, now I'm okay, right? That bundle, the remaining bundle, I don't care. All right, it's not better than mine. Then it's okay. All right, so envy-free up to 1 is a bit has a bit twisty nature here. So any question about envy-free up to 1? How to choose G? Now, very good question, right? Now, because it's additive, right? Because it's additive. So which G do you think I should choose in order to easily satisfy EF1? Very good, okay? Largest, right? Okay, largest one. Okay, now, so this is the rationale, all right? When you try to measure whether it's EF1, this agent will always choose the largest item, right? Or the most valuable item from the other bundle, right? After you throw away that, then the envy-free property will be easier satisfied, right? Okay. Okay, so this is EF1. Now, let's look at the one very famous algorithm. All right, this algorithm is called round-robin algorithm. Oh, now in fair division domain, you will see many easy algorithms that can achieve good properties. All right, so round-robin, what is round-robin? Suppose we have 3 people, all right, blue, orange, green, all right, and we have so many items, all right, apple, orange, grape, etc., etc. So round-robin says, blue player, you can choose first. Okay, so they are choice-based. The blue player choose an item. Now, which item does he choose? Definitely the most valuable item, right? So blue player, so any player, he or she will choose the most valuable item in the remaining set. So the blue player chooses cherry, the most valuable one, to him, her, right? And the next one is orange player, right? And next one will be green player, and so on. Okay, and then we go back to the blue one, let him choose again, and then eventually you have this allocation results. Okay, now you see it says a round-robin algorithm is EF1, which means this allocation is EF1, right? Okay, so basically it says nobody will envy other up to 1 item. Now, this round-robin algorithm Firstly, you see the blue one will never envy any other people. Why? The blue one will never envy. Why? He has 3. Well. Remember, those items mean differently to them, right? 3 items that not so. Okay. Well, so now I see some follow-up answers, right? So basically, the blue one picks first. So he picks the best one, right? He chooses the best one in that round. Now that means the cherry means the most to the blue player, right? Cherry means the most to the blue player. Okay, so that means cherry is better than apple, and cherry also better than orange, right? Grape is better than the avocado, and then grape is better than watermelon, right? So basically in every round, the blue one chooses the best item among the items all the people choose. Okay, and then because we are doing round robin, so as long as there are somebody choosing in that round, the blue one must have chosen something, and that something is the most valuable in his eye, right? Among all the items in that round. So what? So that blue one will never envy other people because his bundle is the most valuable, right? In his view. Okay. So now the point is, it's easy to show blue one does not envy other people. But how about the orange one? Orange one didn't pick the best one. That's a bit tricky, right? But the good news is what? The good news is we are not talking about envy free. We are talking about envy free up to 1. So when we talk about the orange player, yeah, so if you remove this item, right? If you remove the cherry from the blue one, then you look at the figure. You see, actually for the orange one, he or she take the best among the 3 items here, right? Right? This time, yeah, so as Ian said, right? This round, start from the orange one now, right? And then the orange one always dominate in the remaining items, right? In the items in that round, in that so-called round, right? Okay, so that means, well, orange one does not envy other people up to 1 item because he already deleted, right? Removed 1 item from the blue guy, right? Okay, and then green. Oh, green, then I just remove the 2, right? Because I can remove 1 item from each from a bundle from other people, right? So I just remove the cherry and apple. Okay, and then the green one, you see, right? Okay, I'm the best, right? Oh, this one is I'm also the best. Okay, so that explains why round robin algorithm is envy free up to 1. Okay, well, yeah, a long time I didn't launch anything. Yeah, so there's no assumption about 3 people having the same ranking. They do not have the same ranking, but they are picking items according to their own valuation. Whenever it's their turn to pick, they will pick the best one in the remaining items. So basically that means in the view of the green player, watermelon is the best among the 5 remaining things. Okay? So in the viewpoint of the green one, when he picks the watermelon, he thinks it's not watermelon, it's orange. So when he picks the orange, right? Orange is the best among the remaining items. Okay. Yeah. So now, well, just a very simple poll. Did you follow why this one is EF1, MA free up to 1? Very good. But still, there are some who didn't follow. Well, but that's fine. I guess we will just move on. In case you have questions, you can also ask it during the last hour. Okay? Yeah, thank you. Well, so let's move on. Now, okay. Now, Wing Chong asked, are there any fairness issue about deciding who pick first? Well, there is, just like cake cutting, right? So there's always fairness issue. Who moves first? Who moves second? There will be something. So this, I guess people didn't take that point quite seriously because they say, oh, as long as it's MV free up to 1, as long as it satisfies our definition of fairness, then it should be fine. But you are very correct that which one makes the first move did make a difference for the fairness. But there are different efforts to address that issue. For example, you may say, for the person who choose last, maybe I'll give him or her some extra compensation. All right, that may be possible. Well, but that's another story. But that's a very good point. And then actually, this slide is showing some other concern about EF1 and efficiency. Okay, we know EF1 just means that the people will not envy other people if they are able to remove one item from other people's bundle, right? Okay, but how about efficiency? Well, efficiency means how good the solution is. Now, efficiency can be the total value of the items to the people who are allocated those items. For example, you say, okay, I get an item who the value I think is 10, and my friend get a value who the value an item the value he thinks is 20. Okay, so I try to add up all the values together and try to make the value as big as possible. All right, so there are some measure which says, okay, I can add up all the values of the items to the player who is holding them, right, and try to maximize that. Well, so that one is one reasonable measure of efficiency, right? Now, second measure is, well, I try to make the one who gets the least value not too sad. Okay, for example, there is one person who got only value 2. Then maybe that person is very sad. You say, okay, maybe we are trying to maximize the minimum value each player get, right? So that's a maximize the minimum. But here we are talking about another concept called Nash welfare, which is a balance between the total value and the minimum value. Okay, what's the Nash welfare? Nash welfare is people's value. You multiply them together. Okay, so you can imagine that if the solution, now you can see that if you do a sum of VI, then even if the whole sum is very big, there could be someone who is very bad, whose value is 0 probably. Okay, though that may not be that good, right? Now, but if you embed that solution to Nash welfare, then that value will be 0, right? Because you see, this is a multiplication, right? As long as 1V is 0, the whole thing is 0. Okay, so if you try to maximize Nash welfare, you will not see a solution where 1V is 0, the other V's are very big, right? Because that solution may not be that good, right? It may not be that fair. And another one, now remember, we mentioned 2 objectives. One is the sum. The other one is I can try to maximize the minimum of V. Right? I want to make the smallest V as big as possible. Okay. Now, this Nash welfare actually can somehow address this issue too. So, if your smallest V is very small, then the product will not be big, right? So if your product is big, then very likely your smallest V is not too small. Okay, so this Nash welfare measure can combine the benefit of the sum and the mean objective. Okay, now this sum and the mean, we'll see it a lot of times in the coming lectures, so keep that in mind. If you talk about efficiency, the two very natural measure will be adding up the value of all the people together, or you try to maximize the minimum value of each individual, right? Okay, and then Nash is some kind of combination. He tried to maximize the product of all the values. All right. Okay. Now let me erase my writing here. Okay. Yeah. So the Nash welfare measure, if some solution can maximize the Nash welfare, then we call it maximum Nash welfare solution. And this solution is always Pareto optimal, which means we cannot make somebody better while other people do not lose. Why is that? If a solution is maximum Nash welfare solution, then why it is not possible to improve somebody's V without hurting other people's? Okay, I see some answers, but well, it's easier than that, right? The solution should be easier than what you argued here, right? Now, it's some kind of proof by contradiction, right? Contradiction. So you have a solution, right? If it's not Pareto optimal, if you can increase some V without hurting others, then the whole product will what? Will increase, right? Oh, then it's no longer max. Okay, so that's the argument. It's very, very easy, right? Okay, yeah. So now let's go on. All right. So it's very easy to see that this is something like good solution, right? That's a good solution. Okay. And then well, there's a 2016 result showing the maximum Nash welfare allocation is always MV free up to 1. Okay, so that proof is so I remember that in my group meeting we talk about this proof too. All right, so it's not difficult to derive, but takes some effort. All right, okay. Now we define a second relaxation of MV free. Just now we talk about MV free up to 1. So now we talk about MV free up to any. All right. What's the difference? The difference is earlier I will choose one item to take away from the bundle. Now I said, okay, I'm more ambitious. Okay. It should not be the case that I take an item off and then I no longer envy. It should be the case that no matter which item you throw away, I will not envy you. Then I say it's EFX. Okay, so mathematically, so Wing-Chun asked a very good question. There always exists an EF1 solution. Yes, you're right, because maximum Nash welfare solution must exist, right? Okay, very good point. Now, so for EFX, you see, well, no matter, so you see this difference, right? The only difference is here. For EF1, it's there exists a G, right? For EFX, it says for all the G, no matter which G, I remove it, I no longer envy you. Then it's EFX. So in other words, in EFX, which item I will pick from the other person's bundle. Yeah, very good. Okay, so now I see there are many answers here. The smallest, very good. Okay, you will pick the smallest item to remove because if you remove the smallest item, I still do not envy you. Of course, if I remove other items, I also will not envy you, right? Okay, yeah, good. Now let's move on. So let me see whether there's any question. Okay, now there's a very natural question too. Just now, Wing-Chun said, well, the earlier theorem implies that EF1 allocation always exists. Now, of course, there are other ways to prove it, but that is one possibility, right? One possible approach to prove EF1 allocation always exists. But how about EFX? Will EFX allocation always exist? Well, so actually, this is one of the biggest open question. Okay, the biggest open question in the fair division domain. All right. Now see, SODA is also the top theory conference. So in SODA 2018, people showed EFX allocation exists for identical monotonic valuations. Okay, identical means people are the same, players are the same. All right, and then monotonic, that means I get more item. Well, my value is more, right? So they only show that EFX exists for this kind of valuation. And in EC 2019, so EC is the top game theory conference in the CS. Okay, so they show that, well, EFX exists with a good Nash welfare guarantee if donation is allowed. So donation means what? Well, donation just means the throw away something, right? So in divisible case, for cake, right? You say, oh, some piece of cake I can throw it away. I do not give it to any people. So for indivisible case, it just means that some item, I can throw it away, all right? I do not give it to any people. And then I guarantee, well, you have some kind of EFX allocation, all right? Such that the welfare is good, right? Social welfare is good. Now you see, this is very recent. It's only 3 years ago, or maybe 2 years ago. Now, actually, there's also a more recent, donation just means throw away. Well, you do not give it to people, right? Well, anyway, you do not give it to the people who are playing the game. You give it to some charity, all right? Okay, so so it's kind of throwaway, but actually it's not throwaway. It's giving the things not to the players playing the game, right? Or not to the agents who are in your fair division scenario, right? Okay. Now, more recent, EC 2020. Okay, they showed EFX exists for 3 agents. Well, when you see the title, when you see the results, you may feel very surprised. Oh, only 3 agents. They show EFX exists. It can go to the very top conference. Well, that means that the community really looks for, thinks this problem is very interesting because EFX exists for 3 agents may give some sign to the general existence of EFX, right? Okay. Well, so I guess then I will just make a very brief start of the remaining topic. Well, I guess I will skip some of it for the interest of time. Okay. Now, up to now, we have discussed about the divisible goods and indivisible goods, right? And in divisible goods, we have MV3, and indivisible goods have MV3 up to 1. Okay, so how about if these two things are somehow combined? In other words, we are allocating not only divisible goods, but also indivisible goods. All right, what will happen? Well, how to define the MV3 measure? Okay, now more mathematically, you see we have M indivisible goods, right, and 1 divisible cake. And then each agent will have a valuation function for indivisible goods and also a density function for cake. And then your allocation consists of 2 parts, M for indivisible goods, C for the cake, right? And your value of the bundle is summation of the value of the 2 parts you received, right? So up to now, I guess everything is very standard, right? Very standard. Now, how to define MV3? Well, should we use the MV3 concept or MV3 up to 1 concept? Now, maybe one approach is that for divisible goods, we use MV3 because, well, that's a very widely used in divisible goods case. And for indivisible goods, we use EF1. Can we do that? So one example shows that it's not so reasonable. Why? Because you see, now we have a house and $10. Well, of course, let's just pretend that the house is very cheap. Okay, every person thinks the house is worth $2. Okay, and then you see, for indivisible goods, you can only adopt EF1, so I give the house to the blue player, right? And then for the divisible goods, which is $10, I make them half, $5 each, right? $5 each. And then this division, this kind of allocation satisfies EF1 for indivisible goods, and it satisfies MV3 for divisible goods. Now, is this allocation good? It's actually not, because you see the red player, the orange player is not happy because they get $5 each, but the house is here, right? So a better solution will be give $4 to the blue player, $6 to the orange player, because the orange player also thinks this house is worth $2. Then he will think, okay, 6, that's a good, right? That's a good allocation. So that means using the simple combination here does not make sense, right? And that's why in their AAAI 2020 paper, Xiaohui, their group introduced a related concept, okay, or a very good combination of the MV3 concept. And actually, that paper won the best student paper in AAAI 2020. Now, so the relaxation is something like this. Right? If agent J's bundle only consists of indivisible goods, then it's okay to adopt EF1. All right. So then for agent I, You say, okay, then since my partner, right, only get indivisible goods, then I'm fine with EF1, all right? Remove one item. Otherwise, I will be very strict. You say, okay, if you also get some indivisible resource, then I will require my valuation to be at least my valuation towards your bundle. Okay, so this is also a very natural extension. It says that if my envy partner, right, my envy partner didn't receive any indivisible resource, then I adopt the traditional EF1 for indivisible resource, right? Now, if he or she ever get anything, any money, right, any divisible resource, then I will be very strict. Okay, then I need my value to be at least my value towards your bundle. Okay, you cannot escape anymore. All right, I will adopt envy free. Okay, so this is the another dimension of generalization, and this actually this new concept, it will reduce to EF in the divisible goods case, and it will reduce to EF1 in the indivisible goods case. Okay, yeah. So I guess I will just state the main theorem, and I will leave the high-level explanation of those deductions to the next lecture. Now, the main theorem is an EFM, right, mixed allocation, always exists for any number of agents and can be found in polynomial time. Okay, so that's a very elegant theorem. Okay, so I guess today I just stop here, and then we'll move on to the tutorial session. We'll explaining the answers for tutorial and also Q&A after the break. So we have 5 minutes break. Now feel free to ask questions also during the break. Yeah, so there's one question about doing recording and take pictures. Yeah, so if you only have one smartphone, I think it's okay to use it to record at the beginning. And when you are about to take photos, you need to let me know. And at that time, we will use the first device to monitor the process. Okay. So that means that make sure that when you take pictures, your first device is capturing you taking the picture, right, before the camera. By the way, for the answers of assignment 1, I will double check today and then may release it within today. Okay, so that you can review the answers. Yes, you need to record, not record the Zoom, okay? You need to record your midterm answering process using a second device and then submit the video. Okay. Since all of you are postgrad students, now I'm not sure master student whether you can use a Zoom cloud recording. Yeah, you are raising a very good point. So please double check, right? So according to what I know, a PhD can use cloud recording function of Zoom to record your second device. But not sure about master student. And also, if you choose this option, I need to put you in separate breakout rooms because the second device, because I'm not intending to ask you to connect the second device to the Zoom. So if you want to use cloud recording, you need to tell me beforehand, right? So that so that you will use the second device to join Zoom, but I will allocate you to some breakout rooms. Oh yeah, so open your own Zoom. Yes, you're right. You can also open your own Zoom and let that camera capture your exam answering process. That's also okay. Yeah. That's okay. Yeah. Yeah, the requirement quality of recording quality will be 720p, but someone told me that 720 has a very low resolution. I don't know whether it's true or not, but just one thing, okay? So you need to make uh, this the video quality um, reasonable, okay? So basically, you can try to record first and try to view it by yourself. If you are satisfied with that, then it should usually be fine. Yeah. Okay. Now, let me share the screen of the Word document. Sina, you are right. The second device, as long as it can record the angle and the necessary components of your exam answering process, it should be fine. All right. Yeah, especially if you can use Zoom cloud recording, it will be very ideal. All right. Le Tian asked for, does triple AI 20 imply the polynomial EF protocol for cake cutting? I guess it's not for cake cutting. It's for divisible and indivisible resource, right? The polynomial envy-free protocol for divisible and indivisible resource. Well, but again, there's some trick in the statement too. Okay, and also it's not the. Yeah, you are right. And let me. Yeah, you raise a very sharp point. Yeah, it basically assumes some oracle for cake cutting. So there is some trick play there. Okay, so they assume that there is a perfect cake cutting protocol which can be used as oracle. Now, if you do not have that, then only approximate EFM can be found. So did I answer your question? Yeah, thank you. Okay, so now let's move on to the tutorial explanation first. Let me share the document. Okay, so this is the document, the tutorial document. I don't close this one. Yeah. Okay. There are 4 questions in the tutorial, and question 4 I'm not going to explain. All right. So because yeah, the only thing I can tell you is it is a greedy algorithm. All right. You may try to prove what kind of greedy will be there. Right. And then the first question, construction of bridges. Now, construction of bridges, it says that you have n points above the river, n points below the river. Remember, they are not sorted. Okay, they are. It's not like b0 less than b1 less than b2. It's not true. Okay, that there is a predefined connection requirement, like a0 has to connect b0, a1 has to connect to b1, etc., etc. Okay, and then the question asks you, what are the so what are the largest number of connections you can make without crossing each other? Okay, so let me share a whiteboard. So it's basically something like this. Points here, and you have another kind of points below. Okay, and then certain red, and so there are some possible connections. Only those connections. Okay. All right. So now your task is to find out how many crossings, right? At most, how many crossings you can have without them crossing each other. Okay, how to solve it? Well, I didn't mark the in-class exercise now. I will ask my TA to do it over the weekend. So, any solution you have proposed in your in-class exercise? So this one is oh, okay. Yeah, in some sense, okay. So basically, it's a DP, right? And then well, but yeah. So for now, because order by position. Okay, yeah. So basically, the now one thing, if you do not link it to any sequence problem, all right, it can still be done, right? So of course, reordering is also good, like Yanni and Sri mentioned, right? So you can transform it to kind of a longest increasing sequence, or yeah, so problems like that. And then if you do not have any such transformation, it is still possible. The reason is actually you can do DP and only consider state, which consists of the string, the sequences starting from somewhere to somewhere else, and then starting from say well, maybe this place to other places. Okay, so basically it's when you locate one thing, for example, you say, oh, for this node, right? You have an option to match it or not match it. If you do not match it, you have a subproblem dealing with this piece and this piece, right? If you match it, then basically all the things before that green top dots will be useless because you do not allow any crossing, right? So if you decide to match it, all these things will be gone. If you do not match it, then you are dealing with a smaller problem with this node removed, right? Okay, so this is the solution. It's a DP solution. Now, of course, you can also, as Yang and Sri said, can transform it into a string problem, all right? A more string problem. Okay, and let me do the second one. Okay, optimal strategy for a game. Okay, so this one says that you have a row of n coins. The value is from v0, v1 until vn minus 1, and the two players will take turn to take either the first coin or the last coin. All right, and then player 1 starts game. Determine the maximum total coin value player 1 can win. Right? Okay, so this one I think this is also not difficult. So again, it's you have a sequence of coins here, right? And then actually player 1 only has 2 choices at the beginning, right? He has 2 choices, either take this coin or take that coin, right? After taking a coin, the remaining problem is a contiguous piece in the interval, right? For example, if he takes this coin, then you only need to consider this part, right? If you take the last coin, you only need to consider this part. So they are status, right? They are the states in the DP, in dynamic programming. And then, of course, this interval, right? So because now usually, all right, usually when you have an interval and you have the option of 2 players, then you need to add another index. For example, you say, my status is something like this, D, and then the range of interval I consider, right, from I to J. And then you also need to specify which player is moving, 1 or 2, right? Just like when we talk about the tree case. But in this problem, specifying which player moves next seems not useful. Why? Specifying which player moves first seems not useful. Oh, moves now, right? So if now you are talking about this interval, right? You're talking about interval ij, the coin between I and j position, right? And then you say, I should also specify now who are moving, right? Who is moving? Do I need to? Jinsong said they use the same strategy. Okay, well, so well, of course, I also do not know the standard answer, the so-called standard answer. But here, actually, you know who is moving. Why? Because it depends on how many coins are left. You have an even number of coins. So whenever the remaining piece of coins, it's an even number. That means player 1 is moving, right? If the remaining is an odd number, then player 2 is moving. So based on I and j, you already know who is moving. So there's no need to add this extra dimension, right? Okay. Yeah, so this is the second DP question. Okay, so let me see whether. Okay, yeah, the third one is called longest increasing subsequence. So it seems from Yang answer that this question is related to the first question. Is that right? Now, firstly, longest increasing subsequence means that you have an array, right? And then you want to pick a subarray. When the index increases, the value increases, right? You want the subarray to be as long as possible, right? Okay. So, well, I didn't realize the connection earlier. So it's very good that some of you realized the connection. And yeah, so for me, I will not explain it here, the connection here, but definitely this can also be done directly, right? By doing, by deciding whether you will choose a certain item or not, right? So if you choose a certain item, then you will set a threshold for the future numbers, right? If you pick 6, right? And then the later choices will have to be larger than 6 or yeah, something like that. And then if you do not choose it, then no change. You just remove this element, right? Okay, yeah, so I see another answer. Very nice. So basically, I think I will not explain here, right? But the connection I will not explain. But well, it's very nice to see that some of you have observed some connections to existing problems. That's very nice. Okay. Now, as I said, question 4 I will not explain. Right, but the hint is greedy. All right, so this one is using greedy. Okay, so the remaining time I will leave it for Q&A for all the topics we have covered up to now. Now, one thing I would need to clarify about the midterm. Some of you asked me about approximation ratios. Actually, in the topic for approximation algorithms, the ratio is defined in some way which might not be consistent with some examples. So this one you can rest assured. Basically, especially for approximation algorithm, which I'm going to test you on, we will give the definition of approximation ratio in the exam paper. All right. So basically, because it's a closed book exam, we will give necessary definitions which may give confusion. All right. But it does not mean we'll give all the definitions. Now, what does it mean? For example, I do not need to give you the definition of Shapley value. All right. Okay, so this is one example I'll give you. Okay, so now question time. I can bring any slides up. All right, so all the lectures we have up to now. All right, you have any questions, you can raise it here. Oh, assignment 1. Well, now I can generally explain assignment 1, but since I'm going to release the solution very soon, so I think probably I will not explain in detail. So the assignment 1, actually the only tricky question is the first one. All right. Let me open the assignment document. Wait for a moment. Okay, so let me just explain the question 1, something in assignment 1 first, and then I'll answer your question, the remaining questions. Let me share. Okay, this is the one. Okay, so I guess you can see assignment 1 now. Now the only tricky thing is the first one. All right, the first one. It's about processing jobs, and then the job processing time is dependent on the position, right? Now, actually, the simple answer, all right, which does not get full mark, is that you sort it greedily according to some order, right? But that one only applies to the case when AI is larger than 1. Okay, So when AI is larger than 1, which means the base here is larger than 1, then it's correct. All right. Now, but if the base is less than 1, it's no longer correct. And actually, some of you proved another complicated greedy will give the right answer, but actually it's not true. All right. So some of you give examples why no matter how greedy you do, it does not work. And so if you can show examples like that, you already got full mark. Now, of course, if you propose a solution to solve that case, it's also good, right? But I will not explain the solution here. I guess I will release the answer after the session, after I check again. All right, so this question 1 is the most differentiating question. You need to consider different cases. Now, it's very good. Some of you send me email asking about what's the range of A, right? So that means you already thought about this problem, this issue. And question 2 is a bit standard. It's just ordering the face according to some order, and then you can do dynamic programming. Okay, and question 3, divide and conquer, is also a bit standard one. Yeah, so you will know you will know how to do it if you didn't earlier by checking the answer. That one is also not difficult. And then question 4 is a bin packing problem. And then the first question asks you to prove NP harness. Well, this also comes to the questions some of you asked in the chat. Okay, so will the proof of NP harness be tested? And then Wing Chong said, remember, it will not be tested. Yes. Okay. Le Qian is also correct. Okay. Basically, for the NP harness, I will only test you in the assignment, not in the exam or quiz. And then there are 2. Okay. So Shenyan asked about pop-up in-class questions, and then Xinran said about those questions, randomly remove one item of. Okay. About knapsack, right? About knapsack, actually the answer for that one is no. So sometimes it will give you, it will not give you the optimal solution. So remember the algorithm, the algorithm is kind of removing one item and putting back some collection which fits the knapsack capacity, right? Okay, remember it's only removing one. So there are examples where removing one will not give you a good solution. Okay, so there are counter examples. Now remember also there is a criteria, right? So this process will stop if removing anyone and putting back a package does not improve the solution. Then the algorithm stop. It will stop. Okay. Now if there is no such condition, well, probably it's still okay. It's still okay. But with that constraint, it's not okay. All right. So that's about the answer to the remove one item and putting back a bundle which fits the knapsack capacity. All right. So the answer is you can find an example where this algorithm does not give you optimal solution. Okay. If it's random remove multiple items, I believe there is always a chance that you can find an optimal solution. Okay, so this one, if you remove multiple, well, I'm not able to construct the counterexample. Most likely, there is always a chance that you can get the optimal solution along the way with some probability. Yeah. Okay. Yeah, and Le Qian said the multiple item might not be polynomial. Well, yeah, it's also true. Okay. And as I promised earlier, right, midterm will have more questions on game theory. So I'll try to make sure that that part takes more than 50%. In the exam, oh, okay, it's a very good question. Okay, in the exam, the focus will be given to lectures starting from today. Okay, so basically, you could expect the majority of questions come from fare division, facility location, scheduling. Okay, but earlier parts will still be covered in some sense. So the reason I say majority is that you could, yeah, because the midterm already tested your knowledge about the earlier topics. So final exam, I would test you more on the last 3 topics. Now, of course, when I test you on the last 3 topics, you can never escape approximation, online, or something, right? So especially cannot escape approximation algorithm, right? Because no matter which topics we talk about, there is always approximation inside. Okay, so Jianchong asked, what's the difference between 2 competitive and 2 minus 1 over m competitive? Yeah, so if this is about machine scheduling, then this m is number of machines. Now, in this case, you see 2 minus 1 over m competitive is better than 2 competitive, right? Because it has a smaller ratio, right? But when we talk about lower bound, we say, okay, it's not how much competitive. Well, it cannot be done better than how much competitive. Then if you are able to show 2 minus 1 over m, then because m can be arbitrarily large, so it's somehow equivalent to showing that you cannot do better than 2 competitive. All right. So when we talk about lower bound, then 2 and the 2 minus 1 over m is in some sense similar. But when we talk about upper bound, it's different. Okay. Next question. Is it possible to have an exam later? Well, about exam time, it's not decided by me because at the time they collect the preference. I didn't say any preference about this course because well, sometimes people for large classes they will try to be earlier examined, but for small ones they do not have any constraint. So just the central arrow will schedule the exams according to different constraints. So basically, changing the date is not possible. So the measure you could take is to review earlier. Now, but I understand that the lecture, right? So the lecture is shifted somehow due to my unavailability. So that one I can compensate, right? So basically, I can choose not to test the materials covered in the last week, so that it will be still fair to you. All right. So that one is okay. And then I see a question. The proof I see in page 26. Oh, okay. You're talking about the online algorithm, right? So let me just take that. Online algorithm. '26. Oh, this is a very good point. Let me just double check. Yeah, you're right. So actually the proof on page 26 of the online algorithm slide, it is proving two approximation. But well, you can prove 2 minus 1 over m approximation. All right, so we just didn't put that one in the slide. And Jinpeng asked, I watched the recording of game theory basics for many times. Okay, it's about Sperner lemma, why it can help to solve PPAD. So this one, yeah, actually I didn't dig deeper into the connection. So the way we explain Sperner lemma, it's just saying that finding a triangle with 3 different labels, the difficulty is the same as finding the end of line, right? So Sperner lemma just says there exists such a triangle, but finding it may not be easy. All right, and then because the PPAD is talking about end of line problem, right? There's an end of line problem. So well, finding the end of line given some source will be the same as in the Sperner's lemma, the scenario described in the Sperner's lemma, finding a triangle with 3 different labels, because that will be either a starting point or the ending point of a path. Okay, so knowing this connection would be should be sufficient. So if you can raise further questions if you are still not clear about the connection I just mentioned. And Wing Chong asked, is it possible to make the exam slightly easier? Well, so I think that the exam, now I will cover a very little part for the last lecture's contents, but whether it's easier or not, well, it depends on your performance in midterm, right? If your performance in midterm is higher than my expectation, then I may need to adjust the difficulty of the final exam, right? There's some sound. Okay, yeah. So yeah, so difficulty I can, well, I need to yeah. So basically, you know that you perform very well in the midterm, then the final exam will be slightly more difficult. If you perform not that good in the midterm, then final exam will be a bit easier. Well, so it's up to your performance of the midterm. Yeah, and yeah. So about the, I guess for the online algorithm part, yeah, I think that according to what I remember, the ratio of 2 is easily proved. But if you want to prove 2 minus 1 over m, it may not be that, well, it will be slightly more complicated. And the Xiran is asking a very challenging question, which I do not know how to answer. What's the relation between saddle point in consecutive function and Nash point? Well, I don't know. Oh, sorry. I need to dig at least, not know for now. Oh yeah. About the cooperative game, right? But well, I would suggest you not to play that game, just to reflect your own ability. That would be good enough, right? About the mean and the median of assignment, I do not know the median, but I know the mean. The mean of the assignment is 80. Okay. Yeah. So I agree with the final the last discussions in the chat, right? please do not perform bad in the midterm, because other people will perform good, and then you will lose, right? So it's good. It's always good to be truthful, right, in the midterm performance. Yeah. So actually, I'm trying to see your feedback about assignment 2 or assignment. All right. Do you think 80 is very high? It's too high for the assignment. As I said, the mean is 80. The mean of the assignment 1 is 80. Oh, it's too low. Ah. Okay. Well, anyway, yeah. So that, yeah. So I think that for assignment 80 is fine. Anyway, 80 is already above the usual A boundary, right? So yeah, because assignment you have more time, so I cannot expect to give something like mean 60 for your assignment. That will be too challenging. But higher may not, or yeah, may not be good. Okay. Someone asked me what would be the grade distribution for the course. I don't know. No, there are two questions. The first question is what would be the grade distribution for the course? As I said, I don't know, but I would expect that probably 30% of you can get A range, and then probably 50 to 60% can get B range, and the remaining maybe lower. But it's only estimation. But if you work hard, it could be the case that all of you get above B minus grade. That's also possible. All right. So I do not set any percentage requirement for the. Now so that's why I say your grade actually will not be adjusted according to performance of all students. Your grade is just your grade. Okay, it will not be now. But well, in my course, I only have requirement for A plus. I do not have requirement for A. For example, if you achieve a sufficient grade, you will get A range. But in order to get A plus, that's more challenging. Okay, A plus. Now in my earlier courses, A plus will be given to the students who get a mark higher than, or whose mark leaves the largest gap in the top several percent of students. So which means that now earlier that several percent is 10%, but for this course I also need to consult other other people. Now usually I will be finding a cutting line in the top 10% students. Okay, that cutting line will be the largest gap among those 10% students. So in other words, if someone get an extremely high grade while a good majority clustered below, then only that person can get A plus. Now, if there are 3 to 4 people clustering on the top end, and then the others are low, then I will give A plus to the 3 or 4 people. Okay, so this is the way to give A plus. But for other grades, it's absolute threshold. It's not related to other people's performance. And then Ziao asks, is the difficulty of QE comparable with assignment or midterm? I think the difficulty of QE will be comparable to assignment, not midterm. Okay, because midterm, well, at least not comparable to midterm, easy questions in midterm. Because in midterm, well, we will have some easy questions, all right? But in QE, not, so you can have some easy part, but that part will take a minority, okay? So it'll be more like an assignment. But of course, I understand that you only have 1 hour working on the QE question, so it's definitely not comparable to absolute assignment here. All right, and then what's the average? Yeah, so about Jiankun's question about what's average score of assignment 1, I said that it's 80, right? The mean score. And Ziyao said, according to email, the requirement of the algorithm part in QE contains some other contents from Introduction to Algorithms. How many efforts should we give to chapters in this book? I guess for that book, what you need to know is the data structure part, I think, because this question covers both data structures and algorithms. So data structure part, you can refer to that book, I think. Yeah, algorithms actually in this course we already covered. So you can just refer to those. And then there are, yeah, and Sri asked whether QE will include game theory part. Okay, I didn't decide yet. So even if we include game theory part, it will also be related to algorithm, right? So you know that, for example, for fair division, we also have some problems, right? And for those problems, we also need solutions. Now, even if they belong to the game theory topic, they are also algorithm questions. So the focus will be data structures and algorithms, all right? But these algorithms can have a game theory background. In other words, in the QE question, I will not ask you how to compute Shapley value. That's meaningless, all right? Okay. The book is the MIT book, right? The Introduction to Algorithms. And also there's one other question asked before, is about Q1 of assignment 2. Oh, okay. So Xiran, this question I cannot answer you too. I also cannot answer you. The reason is this question is not made by me. I need to consult. Okay. And yes, Jinpeng, you're right. It means that the approximate online randomized will be included in some sense. But again, yeah. So again, that how to say? So you need to know those things, and you also need to know the basic analysis tools. But yeah, I'm not expecting you to complete a, yeah, QE is for PhD only. I'm not intending to include the very advanced level of mastery of those topics. And there's also a very interesting question. Can we get some bonuses if we complete all 3 problem sets plus OJ problems? This one, I think, for now, we cannot do that, but we can take the highest 3 components of your assignment. So remember, OJ is treated as 2 assignments, right? And then for other assignments, each of them is treated as 1. And then among the 5, the top 3 will be counted in your score for assignment. Okay. So I guess that's already some kind of bonus, right? To some of you. Okay. Yeah. So Jinpeng, you're right. Pass all OJ questions means full mark. You're right. So in other words, then you get 2 100. Yeah, the deadline of the OJ will be several days after assignment 3 is released. So um, yeah, it is definitely not week 11 now, because in week 11 we are doing midterm, and then we didn't even have sufficient material for the for the last assignment. So very likely it will be week 12. And then Jianhua asked, will, will provide some exercise for the last 3 chapters similar to the exam? Okay. This is a tricky question. What do you mean by last 3 chapters? Oh, you mean you mean last 3? Let me see. You mean the things after? Yeah, for sure. Because assignment 3 will be something like this. Okay, so basically in assignment 3 you will see exercises on fair division facilitation games. Okay, scheduling maybe not possible anymore, but yeah. So but in the lecture you will see some problems that are of interest. Um, yeah, and then of course we will have another tutorial for sure, uh, trying to capture some problems, right? And then that one, but that one will be a bit late, maybe after assignment 3 is released. Yeah, okay. So actually, when I checked the recent announcement, I found that in my schedule, we wrote that the OJ will be due in week 11. So which seems not right. I'll update that. Okay. So OJ will be due after we release assignment 3. This is something for sure. So other questions? Recommend book? So which recommended book? Yes. So this is the book for um, the first 4 lectures, right? Or um, it's more about the QE requirement. And by the way, this book has a new edition coming out very, I guess already. Yeah, I remember it's March. So it's the 4th edition. April. Oh, okay. You have a more informative uh, source of information. Yeah, it's very soon. Yeah, so assignment 3 will be released yeah, I guess it will be released on schedule, so which is a Friday next week. But if that's the case, then very likely in assignment 3 we'll only cover the topics in fair division, right? Other things we didn't discuss yet, but it may be possible to put something about facilitation, since the due time for assignment 3 is week 13. So even if it covers something in week 12, I think it's still fine, right? But so you need to schedule a time well. And tutorial 2, I'm planning to release it for the last topic. So that means very likely it will be in week 13. So after we roughly finish the scheduling part. Yes, your second half in-class exercise will be submitted together with tutorial 2. You're right. Okay. Xinran is asking about online algorithm, random algorithm, immatized analysis. Can you recommend some materials or exercise? Okay, so for this part, I think I will try to find something. Yeah, I will try to find something and post it on the course on the Canvas. And about the proof, actually, I would require some simple proofs, and now because in the exam, if it's basically impossible to do difficult proofs, right? So if I require you about the proofs, then they will usually be easier to derive. Okay, so it's not like it's not like a research problem and say, okay, please solve, please show some new results. That's probably not the rationale. Okay. The one thing, for example, for immortized analysis, one type of question could be something like, we explain some examples of immortized analysis, and then there could be other scenarios where immortized analysis also works. And so those scenarios I may not have explained in the lecture. And then, well, when you, for example, in the exam, you may see such scenarios, and you should be able to apply those techniques to show that immortized analysis, immortized running time is something like big O of 1. Now, this part, I cannot tell you which problems are possible, right? So you may explore by yourself, right, to see whether there are some easy to describe problem which also has a good immortized running time, and that will help you in the review process. And this is some advice I can give you. Yeah. Okay. So any other question? Some easy problems from where? I don't know where. Okay. You may explore by yourself. Okay. Are there only short answer questions in exams? Yes. Just like assignment, right? So the questions in the exam or midterm, their format will be similar as assignment. We will not have some kind of filling in blank or multiple choice. Those will not be there. All right, and then remember it's paper and a pen. Okay, basically you open the PDF file, you write your answer on your paper and take photos. Okay, so to be fair to all the students, we do not allow typing because typing is a way more faster than writing for some of you. So yeah, so no typing is allowed. Okay. Senior asks, do we need to learn some graph properties by ourselves? It's not needed, I think. Especially, I would not assume any graph property which needs some effort to prove. Oh, I see. So I guess you're asking the question about the approximation algorithm. They are closely related to graph. But then I actually for graph, what we need is only basic definitions. So I do not think that further properties, further graph properties are needed. You just need to know the basic things like which node connect to which node, their connection, the edge connection, and yeah, degree, etc., etc. So very basic things will be sufficient. And also for some problems, the definitions, very likely I will also give it to you. For example, if I want you to get something for independent set, I will define what independent set is. Okay. So basically, they're very, very easily described concepts, and you do not need to remember those specific things. Okay. Oh well. Yanni is asking a question about whether using iPad to write is not allowed. If you use a now the point is if you write using iPad, I don't know whether it will be clear enough for us to mark. But if you are sure it's clear enough for you to mark, and you're also sure that the recording could very clearly capture what you are writing on iPad together with other screens and yourself, then you can do it as long as you are writing, you are not typing. Okay. Okay. Oh, okay. Shinran is asking how to determine the least call. Well, now determine the least call has two parts, right? You first need to show some epsilon core exists, and you also need to show values smaller than that. Those kind of calls does not exist, right? So that's how you determine the least call, right? But then it will be very challenging, right? You both need to prove positive results. You also need to prove negative results, right? No core, no epsilon core can be found or exist with a certain epsilon, right? Or with a value, certain value smaller, or certain epsilon smaller than certain value, right? Yeah. Okay. So your asks, your second device should capture both your papers and the computer screen. Yeah. So basically, if for paper and pen exam, right, you need to capture your screen, which you use to view the question, your paper, your whole body, including your hand, especially upper body, right? And yeah, because earlier there are also um, well, you know, there are cases many different cases. Just make sure you capture everything and avoid causing suspicious action or causing some doubt when we view your video. Yeah, because you know, capturing the environment is very challenging. For example, it's very difficult to show you do not have a third device. Okay, so try to capture your surrounding in a way that it will not cause any suspicion from us. Okay, so that's the main purpose of recording. So that also means that your head is also very important. Your eyes are also very important. Okay. Okay. Any other questions? So today I probably need to well, leave a bit early. Yeah, today's lesson is over. Yes, today's lesson actually is already over a long time ago. The last hour is used for question Q&A purpose, right? So feel free to leave. And actually, I also need to leave in a few minutes. Yeah. Sina asks, can I simply comprehend pure strategy is a strategy we will always hold, and mixed strategy only occurs in base? Oh, no, that's not true. Pure strategy is a deterministic strategy, which means that you will play this strategy. And mixed strategy actually is not for Bayesian game. Mixed strategy can also be for, though actually mixed strategy is not proposed for the Bayesian game. Mixed strategy just means that I use some probability combination to choose my pure strategies. For example, for scissors, rock, paper game, right? You say, okay, I use 1/3 probability to choose each of them. And this is a mixed strategy, right? So you don't, so for each play of game, you don't know which strategy I chose. But I told you, with 1/3 probability, I choose each of them, right? So in each implementation of the game, the strategy you chose may be different, but they follow this distribution, right? So mixed strategy is also for the game that pure strategy is works for. All right. So I hope I explain myself clear. So did I answer your question, Xiran? I don't know what you mean by you choose a strategy which always against another people. Remember, you are choosing a strategy at the same time with another person. You cannot say you choose this strategy, then I choose that one. You cannot do that, right? You cannot say if you choose that, I will choose this. This is not the way, right? Okay. Instead, no matter what others choose, you have to decide your strategy. And then there's also a question about Nash equilibrium, I think. I didn't have time to check email.
Yes, sir. Can you hear me?
Yeah.
Yeah, the question is, I think, is very similar to Shinran's question. And yesterday I sent you an email and I asked the question. So the dominant strategy means no matter how others choose their own strategies, I always choose the best one.
Yeah.
Okay.
Yeah, but in your email, I guess you didn't ask about dominant strategy, right? You asked PO.
No, I actually asked the dominant strategy.
Really?
Yeah.
Let me. Oh, Pareto dominates. Oh, that Pareto dominates does not mean dominant strategy. Okay, so when you say certain because you said that it's kind of 10-10, whether it Pareto dominates any other strategies. So actually 10-10 is not a strategy. Oh, then I misunderstand you. Sorry.
Okay, then strategy means just one person can decide.
Yeah.
Just
so
one player.
dominant strategy is different from Pareto dominates. So when we talk about Pareto dominates, we are talking about a strategy profile, which means each one chooses one strategy. So for example, I choose S1, you choose S2, the other person chooses S3. This combination, we say it can Pareto dominate another combination.
Oh, so the combination is 10-10. That is
yeah.
So what can be called 10-10?
So 10-10 is a combination of strategies, right? Or a composition of different people's strategies. So it's a so-called strategy profile, right? Each one chooses one strategy, and then they become a collection, right? They become a collection. And this one, you can say it Pareto dominates something. But if you talk about pure strategy, there is no Pareto dominate concept. So there is no Pareto domination for pure strategy. For pure strategy, there is only dominant strategy, something like that. So which means that choosing this one is always the best for the player, no matter what others choose. So did I answer your question?
I think
yeah. So like Xingran said, Pareto dominates is a concept for all strategy everyone chooses. So it's like a pool, right? So basically, you in the game world, right? Everyone needs to choose a strategy, and then suppose player 1 chooses strategy 1, player 2 chooses its strategy 2, etc., etc. You combine all of them as a tuple. Okay, you have several. You have one strategy for each agent already selected, and this tuple, you can say it Pareto dominates another tuple. So like in the example you gave, right? So A1, B1, right? Pareto dominate. A1, B1 Pareto dominates other pairs, something like that. But again, you can only say that, well, for example, A1, B1 is not Pareto dominated by any other person, any other combination. And Jim asked whether dominant strategy means it dominates another strategy or dominate or it dominates. Dominant strategy means it dominates all other strategies of the same agent. Okay, dominates all others. Yeah.
Of the same agent means the combination the combination dominates any other combinations.
Yeah. So Pareto dominate means this combination of strategies dominates any other combination of strategies.
For all players.
Yeah, because each combination of strategies needs every player to choose one strategy. Right?
Okay.
Yeah. Yeah, also you need to dominate all other combinations, all the other combinations. Oh, no, sorry. No. So when we say Pareto dominate, we define relative to another profile, right? Another combination. And then there's another concept. There's another concept which talks about all. I need to double check. Yeah, so I guess if you talk about Pareto optimal, and then it's for all, right? If you say somebody Pareto dominates somebody else, then it's for one, right? For one combination versus another combination.
Sir, could you repeat the sentence you just said?
Yeah, so there are two things, right? Two concepts. One is Pareto dominates. The other is Pareto optimal, right? And then Pareto dominates is one combination versus another combination. So you are comparing.
Oh, that is
yeah,
oh,
yeah. One to one.
Dominate.
This is Pareto dominates. And then for Pareto optimal, then it means that if somebody, it means that no other combination can Pareto dominate this one, and this one is called Pareto optimal, right? So in that case, you are comparing this one with all the others.
Okay.
Yeah.
I see. Thanks.
Okay. Yeah. Good. Yeah. Dominating strategy is for one person. Yeah. Pareto dominate is for the strategy profile. So it needs to involve all people. You're right. So whenever we say Pareto dominates, we are talking about a certain choice of strategy for from all the players, right?
Oh, that means PD is when we, that means PD is we have the other eyes. That means we can see everything, and we just pick the one to maximize the whole unity.
Yeah. So so when you talk about PD, then you basically know each one chooses which strategy, and then you are comparing whether this one is better than the other choices, right?
That means 10-10 in yesterday's example. 10-10 is Pareto dominate.
Yeah, something like that. I don't know whether it's weekly or not, but it's something like that. So 10-10 somehow Pareto dominates others, or weekly Pareto dominates, right?
And wait, Pareto optimal means oh, okay.
Pareto dominates means you need to well, so weekly means you can have equality, right? So if it's not, there is no weekly, then you need to be strict in at least one direction. But I believe that the 10-10 example you raised yesterday is Pareto dominates. It's not weekly, because weekly, it allows every dimension to be equal, right? But this one definitely, in one dimension, it's larger, right? It's not equal.
If 10-10 is Pareto PD, and can it be Pareto optimal? I think it is.
It is Pareto optimal. Yes, 10-10 is Pareto optimal, because no other profile can Pareto dominate it, and therefore it is Pareto optimal. So when we talk about Pareto optimal, we are not talking about people deviating. We are just talking about the choices of strategies. So you see that for 10-10, so in that example, if you choose 10-10, so if for 10-10, it's not possible that
I think a player 2 will choose B2, because if we choose B2, 10 is equal to 10.
But remember, when we talk about Pareto optimal, it's not like a certain player deviate, because that he deviates will hurt the other player. It's not allowed, right? Pareto says that when you improve somebody's benefit, you cannot hurt other people's, right? That is Pareto, right?
Okay.
Yeah. Okay. So feel free to send me email before before the midterm, right? If you have further questions. That
means if someone wants to improve his unity, he can't
sacrifice the others.
Can sacrifice others.
Cannot sacrifice the others. Yeah.
Okay, I see. Thanks, Professor.
Okay. Yeah, thank you. Yeah, so because I have another commitment very soon, so we'll finish today's session. And next week, remember, we will have 1 hour lecture first, and then followed by 1 hour and 50 minutes midterm. Okay, see you next week.